when we look at reactions of arenes, okay, the main reaction that we would like to focus on is going to be the electrophilic substitution reaction. So when you have benzene, okay, if you have the ring structure in the benzene, the ring structure can be only broken, okay, by the attack of electrophiles. Electrophiles are electron-loving species, and they are electron deficient. Okay, so they want electrons. Okay, and then when we react with benzene, there is going to be a substitution reaction. So we call it as electrophilic substitution. So if let's say we look at one example, if you have a benzene and we are going to react with, for example, Cl2, okay, Cl and Cl. Now, this one is going to happen, okay, under the presence of halogen carrier. So the halogen carrier that we need to use over here must be something that is related to this Cl. So maybe you can use FeCl3. Okay, this is going to be the catalyst, or we call it as a halogen carrier, and they will give you this structure, which is going to be a chlorobenzene will be formed, and you are going to have HCl being produced over here. So what we need to do is we need to learn how to write the electrophilic substitution mechanism. So the mechanism of the reaction, they start, okay, with the reaction between FeCl3, okay, with the Cl2. So you need to actually remember what actually happens over here is going to be when the Cl approaches the FeCl3, the FeCl3, Fe2 plus, the cation, will polarize the chlorine molecules. So when it polarizes, so what happens, okay, the electrons will be moving closer, okay, towards one side of the Cl. So this part is going to be delta negative, this part is going to be delta positive. So you need to draw that curly arrow. And this will result in a fission where we are going to call it as a heterolytic fission. So you are going to get Cl dot dot minus and Cl plus. Okay, so you are going to get two things over here, which is going to be, one is going to be the electrophile, okay, the electron deficient species. Another one is actually the nucleophile. So in this case, we are interested with the electrophile. So I will just write down here. What happens is you are going to have FeCl4 minus. So the Cl minus, they are going to actually join with the FeCl3. They are going to give you this molecule, left with Cl plus, which is going to be our electrophile. I will erase this part. Okay. So what is going to happen is going to be, we are going to look at it. Okay, hold on, yeah. Okay, so what is going to happen is we are going to react. Okay, so when it reacts, okay, if I put the benzene and I have the Cl plus over there, so the electrons will move. Okay, the curly arrow diagram is going to show us the movement of the electron. So the electron will be moving. And so from the ring, the delocalized electron, which is in the ring, they will go to the Cl plus, but it's actually the attack of the electrophile. Okay, and that will actually give us an intermediate where you are going to have the H and the Cl. We need to show. And the electrons, two electrons, okay, inside the ring, they will actually go and form the bond with the Cl plus. So if I just put it over there, this one I just put, they form a bond over there. Okay, and then this is going to be the positive charges is going to be shared across 5 carbon atoms. Okay, so the positive charges are going to be shared over there. And what is going to happen next is going to be the electrons needs to come back again, okay, to complete the ring. So there is going to be another arrow, okay, and during that time, heterolytic fission is going to happen. So you are going to get a benzene molecule with the Cl left with the H plus. Now this H plus, they will join again, okay, with the FeCl4, okay, they are going to actually give, okay, HCl, and they are going to get FeCl3 back. So this is going to be the product of the reactions. Okay, this is going to be the products of the reaction. And how do you show the mechanism of the reaction? So if let's say we want to actually draw, okay, the mechanism, please remember, okay, they are going to be the curly arrows that we need to focus. We have done this, okay, so I'm just telling you again. Okay, so what are the things that we need to focus on? Yeah, so even this one, okay, the arrow that I put over there, that is not a curly arrow. It's just an arrow to show that it is going to react with FeCl4. The curly arrow that we are going to focus on is going to be the one that I'm going to mark in the yellow over here. This is the curly arrow that we want to focus. And this is going to be the curly arrow that we want to focus. And as well as this curly arrow. So there are total 3 curly arrows that we are going to focus over here. Okay, so the next reaction, okay, that we are going to look at is going to be the electrophilic substitution as well. But this one is going to be a special, they are going to call it as a special name. We call it a nitration reaction. Okay, because we are going to use another electrophile, okay, that is going to come from the reaction between HNO3, nitric acid, and sulfuric acid. Both of them must be in concentrated form. So they are going to actually give you this electrophile, which is going to be NO2 plus. That is going to be the electrophile that we are going to use. So we need to actually write down, okay, the mechanism. If let's say I want to write down the mechanism of this reaction. So first we start with the reaction between HNO3 and H2SO4. Okay, by the way, nitric acid, concentrated nitric acid, and concentrated sulfuric acid, they are going to be in 1-to-1 ratio. Okay, 1-to-1 ratio. 50% of nitric acid, 50% of sulfuric acid, and they are going to be concentrated. Therefore, they are going to also be known as nitrating mixture. Okay, that's a name for this mixture, nitrating mixture. And this reaction will proceed. Okay, this one, if you balance here, they will give you NO2 plus 2HSO4 minus, and they will give you H3O plus. I think the balancing and how to do, okay, you can actually figure it out later. Okay, but what is important over here is this nitrating mixture, they are going to actually give us, okay, this NO2, okay, NO2 plus, which is going to be the electrophile that is going to be used in this case. So do remember, these electrophile, they are not being produced by polarization. Okay, they are not going to be produced by polarization. They do not require halogen carrier because first of all, they are not halogens. Okay, so if you do not use any catalyst or any halogen carriers, how will it happen? So you need to make sure that this reaction is done under reflux 55 degrees Celsius. So this will be the condition that we need to remember for this reaction, electrophilic substitution involving nitration. So under that condition, if let's say they ask you to draw the mechanism of the reaction, you should know that, okay, same way, okay, you just need to draw the benzene and then you have NO2 plus, the arrow will go there, okay. So what's going to happen? You are going to get the intermediate, okay? The charges are going to be spread along 5 carbon atoms. And then you are going to have the 2 electrons coming from the ring will be forming the new bond between NO2. And then you are, to be exact, it will be forming between NO2, yeah? So this N, so O2. And then you have H. So what is going to be the next step? The next step is going to draw this arrow. Okay, there is going to be a heterolytic fission that is going to happen, whereby the electrons, the two electrons will go back into the ring, leaving the H plus alone. So you are going to get H plus and you are going to get a nitrobenzene. So this is going to be NO2, a nitrobenzene. And what's next? The H plus, okay, they will react, okay, with the HSO4. Okay, do remember this is not a curly arrow, I'm just showing, okay, where they are going to produce again the H2SO4. Okay, so it means the H2SO4 is being formed again. Okay, so you are going to have something like this. Okay, so what is going to be happening over here? Basically, we are going to get NO2, and at the same time, you are going to actually get the H2SO4. Okay, this one, if you want to balance or you want to leave it as H plus, is up to you, but you are going to get this nitrobenzene. And do remember, we need to do this in 55 degrees Celsius, and it must be reflux. Okay, that is going to be for nitration. Now, the next thing that we need to know, okay, is going to be related to, I think later I'll talk about it, okay, after we do the acylation and alkylation. But we also need to know about free radical substitution, because generally when we learn about free radical substitution, yeah, we learn that they are going to work under the presence of UV light, under the presence of sunlight, okay, but there is going to be a difference here when it comes to benzene, because benzene is going to be very stable. So if you want to actually react something, you need to have a harsher condition. The harsher condition that you need to have is going to be, must be using boiling benzene. It means under boiling condition. Okay, so what is going to happen is, okay, if you have, okay, do remember, you cannot substitute, okay, you cannot just simply substitute. Like for example, I want to substitute with Cl2, and I cannot simply use a benzene and Cl2 and expect the reaction to give me something to do with like this chlorobenzene. This one will not happen, okay, unless you have a halogen carrier. Okay, so now imagine there is no halogen carrier, okay, and then we want to actually show free radical substitution. Do remember, free radical substitution only happens when you have, okay, any alkyl groups over there. So not the direct ring is going to be substituted. Okay, the alkyl rings over, alkyl groups over there, they are the one that is going to be involved in free radical substitution. So if let's say I want to actually write down, okay, so this one is going to be under the sunlight, which is going to be UV light. And let's say we actually boiling methyl benzene, okay, boiling methyl benzene, and you are going to react with the Cl2, what we are going to expect to see? We are going to expect to see something like this. Maybe the one of the H will go out. You are going to get CH2Cl, and then the H will form ACl. Now, all this mechanism of the reaction we have learned earlier. Okay, this reaction can proceed until all the hydrogen over here is fully substituted by the chlorine. Okay, so if let's say they ask you, please write down the mechanism of the reaction, please use the same mechanism that we have learned under free radical substitution. There are initiation, propagation, and then the last one is going to be termination. I will actually just write down the mechanism for this reaction. Okay, let's say one hydrogen being substituted. So the initiation is going to be the Cl2 to give you 2Cl dot. This is going to be free radicals is going to be, they are going to be formed under the presence of UV light, and homolytic fission is going to happen. Okay, so propagation is going to be where you are going to have a methyl benzene, okay, methyl benzene reacting with a neutral molecule reacting with free radical. It always works like that. Okay, and then you are going to get, okay, the something like this, C and then one of the H will go out. You will have dot, so H2. There is a new free radical being formed, and then you will have HCl. The next step that we need to draw is the free radical that is being formed, CH2 dot. They are going to react with the, always remember, free radical with neutral. Okay, free radical with neutral. So you see neutral, free radical. Now free radical with neutral. They are going to give you another free radical, okay, and a neutral molecule. So what is the neutral molecule that we are going to talk about? Is going to be the CH2Cl. The Cl will go in, like what we want to see over here. Plus, there's going to be another free radical going to be formed. So that is actually the essence of propagation. Propagation means you're continuously producing free radicals. And how about termination? There's a lot of reaction that you can actually consider as termination. So let's say I want to actually write two steps for termination. Cl dot plus Cl dot. That's going to be Cl2. That's going to be one of the reaction for termination. But let's say in this case, if you want to actually also write like this, also fine. Okay, CH2 dot, let's say react with the Cl dot. Okay, and then they give you CH2Cl. That's also going to be another step, okay, for termination. So this one we have learned earlier. Okay, next is what we have learned recently, okay, about Friedel-Crafts reaction. So there are two types of Friedel-Crafts reaction. One is going to be alkylation. Another one is going to be number 5. I will talk about it later, acylation. So for Friedel-Crafts reaction, please remember, we are going to use the catalyst, in this case, AlCl3. Do remember AlCl3 we have seen before, okay, when we learn about electrophilic substitution involving Cl2 or Br2. I think involving Cl2, instead of using FeCl3, you can also use the halogen carriers of AlCl3. It's also suitable, okay? But here for Friedel-Crafts reaction, we will always use AlCl3, okay? That is going to be the catalyst. So they are not halogen carriers, they are catalysts, okay, catalysts. Now, if you want to look at alkylation, basically you are trying to put a benzene, you are going to change it into something, a benzene that is going to be substituted with alkyl groups, maybe CH3, maybe C2H5. So let's say we want to look at how do we change benzene to become methyl benzene. So this one is definitely going to be using Friedel-Crafts reaction, and the catalyst that we need to use is going to be AlCl3. This is going to be the conditions that are required, okay, to get this reaction ongoing. Okay, now, so if let's say they ask you, okay, please write down, okay, the mechanism of the reaction. Now do remember, they are going to actually produce the CH3 from the reaction between what we call as halogenoalkane. So it means it can be CH3Cl, it can be CH3Br, but in this case, since we are using AlCl3, we will actually focus on the Cl. So these are going to be the reaction, yeah. So what happens to the Cl? The H is going to be substituted, so it's going to be HCl is going to be formed. So if let's say they ask you, okay, write down the mechanism of this reaction. So we need to write down. Now, this is going to be totally different than the polarization that we have learned previously. So here is going to be if you have CH3Cl. So I put CH3, and then I think better if I put it this way, CH3, and then bonded with the Cl. What happens is going to be the Cl is more electronegative, so they will pull the electron. So you do not need to talk about polarization, okay? They are polar themselves, okay? So the electrons is going to be pulled, okay, towards the Cl. So you are going to get delta negative, and this one is going to be delta positive. So what is going to happen? You are going to have again, heterolytic fission. You are going to have the Cl minus, and then you are going to get CH3, okay, plus. So you are going to get two things over here, like similar like just now. And this is going to be the electrophile, and this is going to be your nucleophile. Okay, so what is going to happen? Okay, generally, okay, this CH3, they will attack the benzene. So how about the Cl minus? Okay, the Cl minus, similar like just now, AlCl3, they are going to actually combine with the Cl minus. They are going to give you AlCl4 minus. Okay, so the catalyst, okay, is going to work this way. So they are going to actually form CH3 plus. That's going to be our electrophile. So we put the benzene, and you have CH3 plus, similar. Okay, and then you are going to have intermediate H and CH3. And what's going to be next? Okay, this electron will come over here, and you are going to get methyl benzene, and then you will have H plus. So do remember, when the electron comes in, the two electron comes in, there is another heterolytic fission going to happen. So what will happen to this H plus? This H plus, they are going to actually react again with this AlCl4, and they are going to give you the HCl plus AlCl3 back. So if you want to write, I think just write this. Okay, this is going to be the mechanism of the reaction. Again, if let's say I want to show, okay, curly arrow, where are the position of the curly arrow that I would like to see? I would like to see this curly arrow. I would like to see this curly arrow. I would like to see this curly arrow. Okay, three curly arrows over there. Okay, that's going to be Friedel-Crafts reaction. So how about Friedel-Crafts reaction involving acylation? So involving acylation, okay, that's going to be acyl, okay, or we are going to use acyl chloride. Okay, acyl chloride is going to be something like this. Okay, any R group. Okay, that's going to be acyl chloride. So let's say if I want to actually react, let's say for example a benzene, and I want to actually change this benzene to have this particular group, C double bond O, and then they are going to have, let's say, C2H5. Let's change a bit. Okay, not only CH3, R can be anything, okay, which is going to be CH3, C2H5, C3H7, and so on. Okay, so let's say now I want to actually write down what will be the mechanism of the reaction of this. Okay, so I want to actually write down the mechanism. Do remember, all these reactions, they are going to be similar with this electrophilic substitution. Yeah, so they may have different names, Friedel-Crafts reaction, acylation, and so on. But when it comes to mechanism of the reaction, the way they react is going to be still going to be electrophilic substitution. Yeah. So if I want to actually write down, so here, first of all, you are going to have, okay, the reaction started from the acyl chloride itself. Do remember, it still needs a catalyst, AlCl3. Okay. So you are going to actually have this acyl chloride. Okay, so what is going to happen? The first thing also is going to be the electrons, they are going to be pulled closer towards the Cl. Okay, so again, delta negative, delta positive. So you are going to have a heterolytic fission, leaving Cl dot dot minus plus Cl double bond O, C2H5, and this is going to be plus. And do remember which one is the electrophile, which one is going to be the nucleophile. So in this case, you know that this is electrophile. Now this electrophile, same, if you have a benzene, and then when you have the electrophile C double bond O, C2H5, and then plus, the electron will move from here to there. Okay, basically it's an attack of the electrophile. The next is going to be, you are going to have a intermediate, okay, where the positive charges are going to be spread across 5 carbon atoms, and the 2 electrons from the ring, they are going to be used to form a new bond with this electrophile, and you will have C2H5 over here. And then of course don't forget about the hydrogen. Now this structure must be stable again, so the ring must be restored again. The 2 electrons from the hydrogen now, okay, they will come down to restore the ring. So there is going to be another heterolytic fission going to happen. So you are going to leave that H to become H plus, and you are going to have a benzene which is already being substituted by this electrophile. So you will have something like this. And next, okay, is going to be involving the AlCl3 here. We didn't write the AlCl3. Do remember AlCl3, they will combine with the Cl minus. They will give you AlCl4 minus. So they will react with this to give you AlCl3 back plus HCl. So you can just draw this part is enough. This is the mechanism of the reaction. Okay. Now, let's actually proceed, okay, to the last part. Okay, but before I proceed to the last part, please remember, let's do a recap on the substituted, okay, benzene. Okay, if you look over there, we actually substituted the first reaction where we are going to get the benzene substituted with the Cl. We also managed to get something where the benzene has been substituted with NO2. We also have a reaction where we managed to substitute it with something like CH3, okay, or any R group. We also have managed to also substitute something to do with C double bond O CH3. Okay, so there are a few things that we have learned, but I want you to focus, okay, maybe not the last part, maybe this. Okay, I want you to also focus on this. I want you to also focus on this. Okay, these 3, yeah. So these 3, okay, I want you to focus because, okay, the Cl, okay, the Cl, we have what we call as electron withdrawing groups and electron donating groups. The Cl is going to be electron donating group. Okay, Cl is going to be electron donating group. Okay, I'll just put it over there. Other examples of electron donating group, they are CH3 or any alkyl groups. Okay, I told you to remember 2 examples. Okay, so, okay. If you read more, maybe you can see about NH2. Okay, we also have what we call as electron withdrawing group, where they are going to withdraw the electron from, they try to withdraw the electron from the ring. Okay, so the electron withdrawing group, okay, they are going to be the NO2 group. Okay, other examples maybe CN. I told you to also remember this. Okay, so this one, I want you to remember one thing. What is going to be electron donating group? Another one more is what is electron withdrawing group. But another one that I want you to remember is the activating position. Electron donating group will activate position 2 and 4, but if you want to remember, you can actually put 2, 4, 6 position activating. If you have electron withdrawing group, okay, they will deactivate position 2, 4, 6. So if that position are being deactivated, what other position will be activated then? So it's going to be 1, 3 activating. Okay, basically, if you have substituted reaction, like for example, if we are dealing with a methyl benzene, Okay, if I have a methyl benzene, I want to actually react with the Cl2, for example, and I still use, let's say, halogen carriers like AlCl3. Okay, and then what are the products that I will expect? Okay, I will expect, okay, a mixture of products. Okay, the mixture can be one, I can have chlorine being from CH3, because it's CH3 is going to be electron donating group. They are going to be activating position number 2, so that maybe the Cl come over here. Or I can have, okay, a situation where I will have the CH3 over here, and then I will have Cl over here, 2,4 activating. Okay, I can have this. Or I can also have a situation where I am going to have Cl here, Cl here, CH3 here. Or if let's say there is really excess of Cl2, it means it will activate everything, which is going to be CH3, 2, 4, 6 activating. Okay, this is what is meant. So if I actually change this, okay, let's say, for example, if I change this to become NO2, things will be different. Okay, if I have NO2, I am going to have NO2. I will not get Cl at position number 2. I will get the Cl maybe at position number 3. If I have NO2, maybe I will not get this. Maybe I get the Cl over here. Okay, position 3 and 5. And maybe I will actually get a situation, I think no more. Okay, 3, 5 activating. Okay, 3, 5 activating. So these are the things that you need to actually take note. Okay, no more like this. Okay, so this electron donating group and electron withdrawing group, they will affect, okay, in that way. So the last one that we actually want to look at is going to be the oxidation reaction. Do remember, alkanes will not undergo oxidation reaction generally. Alkanes will never undergo oxidation reaction. But when it comes to benzene, okay, or to be exact, not only benzene, it must be something that is being attached to it. So generally must be alkyl group, CH3 in your textbook. So they say that if you are using, okay, this one I've already checked. Okay, you use alkaline, okay, it's slightly different than what the normal oxidation reaction, oxidizing agent that we use. If you are using alkaline potassium manganate, okay, and then after that you acidify with dilute H2SO4. Slightly different, because normally we say acidified potassium manganate. Okay, so the conditions are slightly different. Alkaline potassium manganate, then after that only you acidify with dilute sulfuric acid. They also mentioned that you can also add acidified K2Cr2O7. Okay, you can refer to the textbook. Okay, what are the conditions that they require. But whatever it is understood that there will be oxidation. Now this oxidation is going to actually make this benzene to change into benzoic acid. What is benzoic acid? A COOH is going to be formed with the benzene. So how many oxygen atom is required in order to do that? Okay, do remember it's still some sort of substitution reaction. When something COOH is being there, H plus is going out. Okay, H plus is going out. So when I want to actually find out what is going to be the number that I need to use over here, do remember there are 2 oxygen here. So I need 2O. But do remember H plus will be also changed into H2O. So it means that you are going to need another O to form H2O. So I will put plus H2O. So here, total how many oxygen you need? 3 oxygen, and it will be balanced. Okay, 3 hydrogen. So you have 3 hydrogen. Everything is balanced. So this is how you balance it, okay, which is the oxidation reaction. Now, questions have came out where they ask you something like this. So you need to always also look out for the type of questions that they will ask. Let's say I have C2H5 instead of CH3, and I'm going to actually oxidize them. I want to know what is going to be the product. Am I going to get a product with 2 carbon, or am I going to get a product with 1 carbon? Jody, what is your guess? Are you still going to get this, or you're going to get something else? Jody? What do you think? Let's take a guess.
Something else.
Okay, generally it's okay if you think that it's going to give you something else, but do remember, okay, that's why sometimes when we learn, we always think about what we expect, but what we expect is not the same here, because in this case, whenever you are using any kind of benzene, like for example, even if you're using a propyl group attached to the benzene over here, when you oxidize, you are still going to get a benzoic acid. This is something that you want to memorize. You are going to get the benzoic acid. So what happens to the remaining carbon? The remaining carbon, they are going to be changed into carbon dioxide and then water, plus carbon dioxide and water. Balancing, I think we no need to learn now. Okay, but take note, they are going to actually give you the benzoic acid, and whatever left, okay, you are going to be giving you the carbon dioxide. Like for example, you supposed to have another 1 more carbon. Yeah, carbon is coming out in carbon dioxide form. If in this case you need another 2 carbon, where the 2 carbon goes in form of carbon dioxide. So this is another one more thing that you want to actually take note. Yeah, so overall, okay, if you look at it, okay, we have learned, okay, total of 6 reactions, okay, involving reaction of arenes. Okay, number 1 is going to be a benzene, how a benzene is going to be converted into chlorobenzene, for example. Number 2, we also learn how to change a benzene, okay, if you convert it into NO2, nitrobenzene. We also learned about how if you have a methyl benzene, for example, when they being changed under free radical substitution, how you can convert it into CH2Cl. We also learned about number 4, how do you change a benzene where you can change it to give the CH3, a methyl benzene, which is going to be your Friedel-Crafts reaction. Number 5, we have also learned about how do you change your benzene to put the acyl group over there, C double bond O, and then the R group, maybe CH3, I put over there. And the last one that we just learned, which is going to be how do you change any form of C2H5 or CH3, okay, a methyl benzene or so on, into a benzoic acid, which is going to be COOH. In this case, they are going to give you carbon dioxide and water. So these are the reactions that we have learned until now. Okay, so I want you to think back. Okay, so maybe Victoria, can you tell me what are the conditions required for all these reactions? Maybe number 1, what do you need?
Is it the halogen
Yeah, the
carrier?
halogen carrier. So suggest one halogen carrier suitable for this. FeCl3, or you can use AlCl3. Okay, these are the halogen carriers. Okay, for number 2, Gabriela, Nicole, can you tell me what are the conditions that you require for number 2?
Reflux and temperature of 55 degrees Celsius.
Very good. Reflux 55 degrees Celsius, and then the use of nitrating mixture. Okay, so the nitrating mixture must be with the ratio 1:1 with the concentrated sulfuric acid and concentrated nitric acid. Okay, so how about the condition for number 3, Arnetta?
Catalyst of AlCl.
Do we need catalyst for this?
Yeah.
Okay, this is going to be UV light. Okay, UV light, and then do we need catalyst for this? Let me check. Yeah, I don't think so. We need catalyst. Yeah, it's boiling only. Yeah, so you do not need a catalyst because it's already, the UV light is already breaking them into free radicals. Okay, so the UV light. Okay, and then they must be boiling methyl benzene. Yeah, so that's the requirement. So these two, they are called as Friedel-Crafts reaction. Okay, Friedel-Crafts reaction, and one of it is called Friedel-Crafts alkylation, and this one is going to be acylation. So in order to do this, do remember Friedel-Crafts. Okay, you use the catalyst, which is going to be AlCl3. Okay, that is going to be the requirement. Yeah, you need to have AlCl3 for this reaction to happen. And how about number 6? Maybe I will call Charlton. Number 6, what are the conditions required for oxidation?
Alkaline.
Very good. Okay, this is the one that I really want you to focus on. Yeah, alkaline. Yeah, not the generally when we say acidified. Yeah? Alkaline potassium manganate, then followed by acidified dilute H2SO4, or they say acidified K2Cr2O7 potassium dichromate. So these are the things that you need to know about the reactions of arenes. Okay,